we'll switch gears and move from eBeam inspection to just some comments on what we think we'll see when we move to the multi-beam era. And one of the things we try to do with modeling is ensure that we have certainly the same model form across a whole wide range of processes and shapes. And certainly with the same process, we certainly want to have the same model form if at all possible across different tools. And so what we'll focus on today is the introduction of the multi-beam system, because this is a disruptive technology. It was certainly brought because of the explosion of shot count in an attempt to reduce overall write time. But the question is that going to impact our ability to have a single model form, or is it going to do something different? I think the slide sort of implies the answer at the end of the talk, but we'll go through and we'll ask a couple of questions. You know, what is it about the multi-beam that may or may not be different from a simulation perspective? What's to say? Then we'll ask what we need to consider in detail when we start to look at multi-beam processes, and we'll see some actual results on modeling in the multi-beam era. So what's different? I put up a schematic from our good friends at IMS. They show this quite often, but it's not a talk on how a multi-beam system works. This is really used as an illustration to see what might be different about a multi-beam system versus a VSP system. Now, the VSP system gives you one shot at a time, and in general, you're going to stick your shot at the edge of where you think your printed feature is going to be. The multi-beam has many, many shots, thousands, hundreds of thousands, up to millions of shots, somewhere between 10 and 20 nanometers wide, and they're not put on the edge of the feature. For lack of a better word, if you're trying to print this circle, you're going to rasterize a bitmap and sort of weight average the intensities. And because you can turn beamlets on and off, you can have a different dose profile over each square, and you build up the dose that would be consistent with printing that circle. All right, well, that's kind of neat. What does that let us do? There's a reason to put a circle in that first slide. And this will sort of segue into Tom's talk later on, but I'll show an ILT picture here. Currently, nobody would try to print this pattern on a VSP machine. And I could advertise D2S, the true mass technology, which will try to do this with overlap shots, but in reality, there's too many shots in here to print this. On the ILT, on the multi-beam tool, when you essentially cover this in 10 nanometer pixels, you're not limited in terms of shapes that you can make. You can write this in the same write time to a very good approximation as to any simplified Manhattan pattern. That's great from a write time perspective, but you can think of doing something a little bit more. And this is where the exciting part of the multi-beam era will come from. A lot of times people will try to enhance hotspots, enhance part of the mask that may result in wafer defects, make them print better. So I can think of trying to put extra dose in this small neck feature so I can get better dose margin, so I can get better repeatability. If I have access to the dose values in this multi-beam system, I might be able to automatically enhance printability. I might be able to automatically enhance linearity. And this really opens up the multi-beam era that I hope Tom will continue talking about. I won't talk about how this can actually be done, but there will be a paper at PMJ in the use of GPU in Mask Writing 2 session. We'll show an example of how you can do this with little to no runtime penalty, depending upon how much dose you want to put into the individual features. Okay. So that's the difference. You're going to get a much different dose profile. Well, then you ask, well, what's the same? And the answer is everything else. All right? The mask process really isn't any different. All right? You can break your mask process into 4 steps. The exposure is the same. You still have dose effects. There's still electrons being scattered inside the resist. Once you're done with that, you can do your post-exposure bake, and you can do your development to get your resist CD. You then throw it in your etcher, and the sizes of features change, and you get your etch CD out. There's no difference here. It's just that the dose profile is a lot more complicated. And this complexity in the dose will result in some differences in the mask modeling that we'll talk about in just a second. So what do we need to consider when we're modeling the multi-beam system? And for this purpose, I'll show some data. It's simple 1D trenches. This is the simplest possible structure you can model. These aren't the only structures we model, they just are the simplest thing that show the effects I think we need to worry about. So all of this data is very simple 1D data, and I'll plot it as a function of two things. I'll plot it as a function of feature width, so you can see what I'm plotting here is a mean to target. It is a mask error, if you like, if left uncorrected, as a function of size. We'll talk about where that comes from. But I'll also plot it as a function of dose profile effects. And this is something a little bit different than you'll see in the multi-beam system. It's a little bit hard to get dose profile effects in the VSB tool. In the multi-beam, it opens us the ability to do this. We'll talk about where these things come from in a second, but let's focus on the shape effects. Now, today, if I look at the shape effect, we can typically separate into two issues. Dose effects, which are dose linearity, we'll talk about that in a second, and etch effects, which show also a size dependence, a sort of a constant size. So if I have a small etch feature, it has a small etch bias. If I have a large etch feature, it has a large etch bias for this particular process, and there's a nonlinear transformation between the two. Now, how do you model this today? Well, I put Gaussians down here, and that doesn't seem to be right because Gaussians are a dose dependence. And in fact, the standard model today, which is a Gaussian model with a constant threshold, uses these Gaussians, which nominally are for the dose, to model these etch effects. When we start getting into more complicated dose profiles, this degeneracy will likely be broken, and we'll find that we're not able to use these Gaussians to control for the etch effects like we normally would. I hinted at the dose linearity problem. So again, now I'm not plotting the etch bias, I'm plotting the resist bias. So this is drawn data minus the resist data. Sometimes it's hard to collect the resist data, but we'll show it. And again, big features, print big, small features, print small. And where does this come from? Well, again, same reason, etch uses Gaussians. Big features, you convolute with a Gaussian. If they're big enough, it looks like a half plane and there's no reduction in signal. Depending upon where you put your threshold, you get no CD change. When you have small features, this Gaussian here sees the other side of the feature, signal goes down, your CD goes down. So this is called the linearity effect. Scattering of kernels that are larger than the feature sizes give rise to smaller CD effects. And again, in the standard 3 Gaussian model, these effects are degenerate with a variable etch bias. Well, there's another dose effect that we want to worry about, and this is that second plot where I talked about dose profile changes. So one of the things that you need to think about is when you're doing multi-beam systems, your dose profile may look a little bit different than certainly the VSB doses. And what I'll show here is I'll show two doses, a single dose here, and then a high dose feature where I'm changing where the edge of the high dose appears relative to the printed edge. So down here I have a high dose that's coincident with a low dose edge, and it gives rise to a very large CD. As I pull that offset back, as I pull this yellow away from the edge of the red to make it effectively a single dose here, this is far enough away, and it behaves like a 1x dose. If you remember the linearity effect being scattering kernel larger than the feature size, as I start pulling this edge away, what I effectively get is a complex dose profile with many large features in many different places, and therefore the precise details of the dose profiles are going to matter for your modeling. And so again, we'll look at our multi-beam system. You can imagine we have many, many small features, and we're going to have a much more complicated linearity effect. So now we know where these things come from. We have dose and shape linearities, which give rise to approximately a 90 nanometer error, depending upon how much dose I throw into the system. I also have a dose profile effect over here as I pull large dose away from the edge, and I get about a 30 to 40 nanometer CD change. Typical modeling structures won't show this to you. You need specialized test structures that actually go in and look at this information. So if you don't know what you're looking for, you're not going to see these effects, but you may then miss them when you start putting these on a multi-beam system. All right, so let's ask ourselves the question, if I want to model this with a 3G system, how well do I do? All right, well, I've reduced that mean to target from 90 nanometers to something small. I kept this on the same scale, so this looks pretty good, right, until I make this thing bigger. And I still see it at about 14 nanometers of model error. Okay, so this dotted line now is here at 0, and any data points away from 0 means I have that much of an error left on my mask that I need to correct for. It's not as bad as doing a complete, it's not as bad as not doing correction at all. It's not as good as what you could get. In particular, this 3 Gaussian model overcompensates the effect of the dose profile effects, and it doesn't compensate enough for the feature width effects. All right, so maybe it's the etch problem, right? I said we shouldn't be using dose to correct for etch. So what if we just simulate the resist part? All right, what if we just take the resist data? What if we just take the ADI data? How does that look? Well, it still doesn't look very good. One of the issues with 3 Gaussian models is it doesn't deal with dose corrections nearly as well. And there was a talk last Baucus or maybe last year at SPIE saying we can use DIL-C to adjust for this. That doesn't help for this either, right? There are more things going on than simple exposure that we need to model. So we go back to our physics. There's more things in this ADI than just exposure. There's some post-exposure bake and there's some development effects. And if you include those effects, then you get a model that's actually pretty good. Okay? So even just modeling resist data, when faced with complex dose profiles, you need things that are more than just exposure. Degeneracies get broken. You need more complicated models in order to get a valid model. All right, well, since we can't use dose for shape, what do we do? Well, let's recap, right? The doses are more complicated. We have a lot more dose profiles. These terms aren't degenerate, right? So what do we do for etch? Well, we can use the standard etch processes that are done in many OPC simulators. We take bias and you use shape effects, things like shadowing and local pattern density, which is one of the LEC corrections on the VSB tools, as well as local radius of curvatures. And if you utilize these kind of standard techniques, you can do a pretty good job modeling the etch features. Okay, so how do we do, right? In the multi-beam era, we understand the physics. We know we need to start paying attention to the dose profiles. We know we need to augment the simple shape effect models with real etch effects. The challenge then is to isolate the right dose effects from the shape effects so we can get a predictive model across a whole wide range of features. We need to do this on curvilinear systems. And just as a marketing, we have a test chip that's ideally satisfied to do this. Our true model has test chips and experience for many years dealing with this type of feature for overlapping shots. We have these things already. We've seen this data before, and if we apply all of the dose and shape effects to one model, we can now, well, this looks pretty good. What if I expand it? We're still within plus or minus 2 nanometers. Okay? Now, I've only showed you simple line 1D trench data, right? Not too interesting, but it also expands greatly to isospaces, 3 lines, a whole host of structures. The dots are calibrated structures. The squares are predicted structures. So this is a fairly robust model across a wide variety of features. So this can be done quite easily. Okay, so I hinted at this, and so the answer is yeah. We're ready for the multi-beam era. The industry is ready for the multi-beam era. But the mask model complexity needs to increase. We can no longer rely on our simple Gaussian models. We have to run a little bit more physics, include some additional resist effects, and separate the shape effects from the dose effects. And so we've expanded this part a little bit to include shape-based effects. And once we do that, we correctly separate shape effects from the dose effects and get a good result. Independent of tool, independent of process. And with that, I'll turn it over to Tom to tell us what we can do with curvilinear structures.